Okay, so in this simple example, basically summarizes the average, the main philosophy of this statistical mechanics. Although we are just looking at our system from a statistical perspective, even though physics is kind of deterministic if you don't go to the quantum mechanics, let's say. But still, we can make deterministic predictions. For example, in this simple example, by just saying that on the average, the particles spend half of their time on the left half and half of their time on the right half, the main conclusion we had actually obtained is that the most probable configuration is the one in which the gas is distributed uniformly. Half of them is on the left, half of them is on the right. And in fact, if we just look at this result, that the average number is just proportional to the average number is just p times n. That basically tells me that if you take whatever volume you take, since this probability is proportional to the volume you have, the average number within that volume is proportional to the volume, with a constant of proportionality independent of the volume. And hence, basically, this tells me that the most probable distribution will be the one in which the particles are uniformly distributed. And the probability of deviation from this average value is basically zero. It goes to zero as 1 over square root of n. So then we can ask, now let's first make some definitions. Now we will be talking about the system in terms of its macro state. Now the macro state is basically the macroscopic observables. Like we know the total number, let's say the total volume, the total energy of the system, the total temperature, we will be talking about the temperature, pressure. So these are our macroscopic observables. They don't really depend on the microscopic details of the individual particles. And then we will be talking about the microstate. This is the state of the microscopic particles. That make our system. So, for example, in our previous simple example, the macro state is the total number and the total volume, or the density, let's say, of the particles. The microstate is the position of each one of those particles. So to say something about the macrostate, at the end of the day, we didn't need to say anything about the microstate. I don't know which particle is on the left or which particle is on the right. But what I know is half of those particles are on the left and the other half is on the right. Then, as in the previous example, for a single macrostate, there corresponds many in the sense of the 10 to the power 20 or more microstates. Then there is the question, for a given macrostate, how many microstates are there? So you see, basically in the previous part, when we said that, okay, half of the particle will be on the left and half of the particle will be on the right, the probability of this configuration is 1. But the probability of any other configuration that deviates from this configuration significantly is 0. So that's basically what was our previous conclusion. Now, if you think of probability, the probability of an event is nothing but the number of ways that event can be realized divided by the total number of events that can be realized, the total number of outcomes. So in the previous case, for example, we have the two particles, all the particles can be distributed onto the left-hand side and onto the right-hand side in, let's say, the probability of, this probability is actually, well, the total possible states, if you think of the total possible states, that how these n particles can be distributed, it's just 2 to the n. Each one particle can be either on the left or on the right. There are two possible outcomes for each one of the particles. We have n particles, so the total number of configurations we have is 2 to the power n. The probability that n of them is on the left is nothing but the number of microstates for which n of the particles is on the left. So this is basically, this was our probability. Now to calculate this probability, well, if you divide by 2 to the n is just a constant. To be able to obtain this probability, we actually need the number of microstates that corresponds to our macrostate. So that will be an important parameter for us, and that number we will be denoting by omega. Let's just for the time being deal with a single macro parameter, the energy of my system, for example. In our case, it was, in our previous example, it was n. So for us, this will be the most important number. And well, as in our previous example, what we had seen was the average value of a given number was the number that maximized this probability, or the most probable number. They were equal. Now, the most probable number for the macrostate, the most probable macrostate, is the one that makes this number a maximum. And that maximum is, as we had seen before, is quite peaked. The ratio of omega between some macrostate that deviates significantly from the most probable macrostate is order of magnitude smaller than the omega for the most probable macrostate. So what we will observe is basically the most probable macrostate which is the macrostate that makes this omega maximum. So that is basically what we are also calling the equilibrium state. So the equilibrium in the statistical understanding is the macrostate that maximizes omega. Well, let me not put the arguments. So that's that's the equilibrium state. The probability of observing my system in a state that's not an equilibrium state will be negligible after the equilibrium is reached. Of course, if you create your system in an unequilibrium configuration, like in our previous example, initially, if you remember, we had this partition which kept all my atoms in a region of my volume. When I remove the partition, that's no longer an equilibrium state. But the most probable configuration, we had found out that after I have removed this partition, the most probable configuration was in which all these particles were distributed uniformly. And once that configuration is reached, the probability of observing any deviation from that configuration will be negligibly small. There's no going back. So if you start from an equilibrium state, it will evolve into an equilibrium state because the probability of evolving into an equilibrium state is 1. And once it reaches the equilibrium state, it will stay in the equilibrium state. Well, this is kind of, it looks similar to the entropy. And in fact, we will see that the similarities are quite much more than this. We will see the relation between entropy and this omega. And the second law of thermodynamics, just in this configuration, in this case, will just mean that the probability of increasing the entropy is 1. Because most probable events happen. When we observe the system, the most probable events happen. The probability of observing other events will be negligible. Now we can just, let's see. Now let's do some applications of this concept. Let us start with two systems. Let's assume that initially they are isolated. The left system has some energy E1, the right system has energy E2. They are fixed. Let's say the macro state is described only by the energy. Then I can talk about the macro state corresponding, the number of states corresponding to this macro, the number of micro states corresponding to this macro state, which will be nothing but omega 1 E1, because there are this many microstates of the left system, times omega 2 E2, and this many microstates of the right system. So if I just combine my two systems, the total number of distinct microstates will be just the product of these microstates. So this is assuming that there's no energy exchange. Now let's see, I will allow energy exchange now. So initially I have these two isolated systems. This is the total number of microstates corresponding to the given macro state. Now if I allow these systems to exchange energy, E1 and E2 will not be separately conserved. The total energy will still be conserved. Omega E will still be the total number of microstates available to my system. And this will be, well, when the equilibrium is reached, I know that the left will have an energy, let's say E1 bar, and the right will have an energy E2 bar. So this will be the total number of states. Well, let me be a bit more precise. This is the total number of microstates available to my system. I don't know what the value of E1 is because they are allowed to exchange energy. E1 can change from 0 up to capital E. So for a given value of E1, that product gives me the number of microstates corresponding to that value of E1. But for my whole system, E1 can take any value between 0 and capital E. There might be no energy left on the left, or all the energy might go to the left. So if I ask for what is the total number of microstates of my combined system, I have to take into account all these possibilities. Now the problem is, not the problem, but the observation will be, look at this value. That product is the number of states for which on the left the energy is E1. The total energy is still E. But that number will be highly peaked because I have a very large number of particles. So this sum will be omega 1 E1 av E1 the equilibrium value, omega 2 E minus E1, the equilibrium value. Well, in this sum, the equilibrium value is just one term. There are many terms in that sum. But one of them will be overwhelmingly large compared to the other ones. When I say I'm talking about overwhelmingly large, I'm talking about orders of magnitudes larger than the other ones. So I can just ignore the other terms. And the sum is equal to this one. Now, how do I determine this E1 average? Well, that's basically the value that maximizes that product. So the derivative of omega 1 E1, omega 2 E2, where I will be defining E2 as E minus E1 average, divided by derivative of that product with respect to E1 when I evaluate that product at E1. No, okay, sorry, there is no average over there. When I evaluate this at E1 average, this should be 0. Let's do the algebra. Derivative of omega 1 with respect to E1 times omega 2 with respect to E2 plus the derivative of plus omega 1 times derivative of E omega 2 with respect to E2 multiplied by the derivative of E2 with respect to E1. This should be 0. When I evaluate this thing at the equilibrium value of E1. Well, this derivative is nothing but minus 1. So derivative of omega 1 with respect to E1 multiplied with omega 2 should be equal to omega 1 times the derivative of omega 2 with respect to E2 in equilibrium. Or 1 over omega 1 times derivative of omega 1 with respect to E2 should be equal to 1 over omega 2 derivative of omega 2 with respect to E2. Now you see, if you look at the left-hand side, it's just properties of the my system on the left, of the first subsystem. If you look at the expression on the right, it is just the properties of my second subsystem. Although in my case, I just imagine just two separate systems which I bring into contact. Well, you can just take whatever system you like, take one part of that system and call it your first subsystem, and the rest as your second subsystem. So this basically tells me that this 1 over omega times d omega by dE, whatever this is, it should be uniform over my system when equilibrium is reached between parts of my system. And keep in mind that this is constant N and V. I'm not looking at changes of the number of particles or the change in the volume. I'm just considering the energy. Energy can be exchanged between these two parts. Well, this is already familiar. You see, when equilibrium is reached, the temperature of my system is uniform. And we had already seen that ds over dE at constant N and V, this is 1 over T, which is uniform over the system. And the above expression I can actually write as d by dE of logarithm of omega. So kind of if you just look at these expressions, you see the derivative of the logarithm of omega is also evaluated at constant number of particles and the constant volume. So I have these two properties, logarithm of omega and S. Both of them, when I take their derivative with respect to energy at constant number and volume, the result should be uniform throughout my system. when equilibrium is reached, kind of indicating that these two should somehow be related. And Boltzmann just said that, okay, they are just proportional to each other. Well, you see, if you look at those two expressions, they are the relations between the derivatives of the left-hand side and the right-hand side of this expression. So, in principle, you can actually put some number, some constant, and still the derivatives will satisfy those two relations. But that constant is 0 because of the third law of thermodynamics. You see, what does the third law of thermodynamics tells us? The third law of thermodynamics tells us that at 0 temperature, the entropy of a system should be 0. Well, 0 temperature corresponds to the minimum energy that our system can have. If we use the terminology of quantum mechanics, that's the ground state. Quantum mechanics tells us that the ground state is unique. So since the ground state is unique, omega is 1 when my system is in the ground state. So logarithm of omega is already 0. If I add a constant here, I no longer satisfy the third law of thermodynamics. So third law of thermodynamics basically tells me that that constant should be 0. Now, of course, at this moment, it's not a proof. I mean, the argument that I had given you is not a proof that they are related to each other. But it turns out to be correct. For example, we will be deriving the ideal gas law, and we will say that actually with this definition, it's consistent with the ideal gas law. Now, the derivation of the ideal gas law is in fact quite easy. You see, what is the number of microstates that my system can be in? Let's just assume I have my ideal gas in a given volume. Given volume, given number of particles, then the energy. Now before starting that, let's discuss some other stuff. Now in this system we only allow the exchange of energy between the two systems. Well, let's just assume we have a different system. And this time we have some movable piston in between. So both volume and energy can be exchanged. But the total volume will be constant. So in equilibrium, by just using the similar arguments, we know that omega 1 E1 V1 times omega 2 E2 V2, for the equilibrium values of energy and volume, this should be a maximum. So if I take the derivative with respect to E1 in equilibrium, this should be 0. But this is nothing but that tells us that T1 should be equal to T2, where the T is 1 over the 1 over T is just the Boltzmann constant times the derivative of the logarithm of omega with respect to E at constant volume and the number of particles. But at the same time, since the volumes can also change with the total volume being constant, now this derivative at constant volume, derivative with respect to V1 of omega 1, let me just drop the energy indices, energy arguments, V1, omega 2 of V2, evaluated at constant energy and in equilibrium, this should also be 0. But of course we are keeping V1 plus V2 to V a constant. Well, basically using exactly the same arguments, this tells me that derivative of the logarithm of omega 1 with respect to V1 should be equal to the derivative of logarithm of omega 2 with respect to V2. So again, this should be uniform. And this quantity is just P over T. P over KT. Again, you see, this is this relations the derivative with respect to V at constant energy and the number of particles. These are analogous to the relation you see from the first law of thermodynamics. We know that dE is equal to T ds minus P dV, or ds is 1 over T dE plus P over T dV. So the derivative of entropy with respect to volume at constant energy and number of particles is just P over T. Well, let's add the number of particles here also. Plus mu dN. This is minus mu over T dN, mu being the chemical potential. So basically, you can just repeat the same argument. We have two different systems, but this time they can exchange volume and also the particles. Yes, this is kind of nice because this, when you are taking this subsystem, I can just imagine the air inside my hand. This is a subsystem. That subsystem exchanges energy with the atmosphere in this classroom, and it also exchanges number of particles. So I can study such a system. Now, again, I will not repeat the derivation, but the derivation basically will tell us that derivative of the logarithm of omega with respect to the number of particles at constant energy and volume should be the same throughout my system. And this will just turn out to be minus mu over KT. Now let us look at the ideal gas. I have my ideal gas. It's at some energy, some volume. There's some number of particles over there. So how does omega depend on V? What would be your guess? You see, omega is the number of this microstates that my particles can be. Well, you see, the definition of the microstate also involves the position of my particle. So my particles can be, the number of positions that my particles can be at is proportional to the total volume. I have n particles, so this should be proportional to V to the n, with some proportionality constant that will depend on E and probably n also. Now, derivative of, let me just take the logarithm of omega first. Logarithm of omega is n times logarithm of V plus the logarithm of f. Well, keep in mind that this is true since I'm assuming that the particles are independent of each other. So the probability of one of my particles being in one position or some other position should be independent of the positions of the others. Only in this case, the number of states that a single particle can be in, the number of positions that a single particle can be in, will be proportional to v to the n. Well, the derivative of the logarithm of omega with respect to v at constant temperature, at constant energy, and the number of particles, if you just look at this expression, this is just 1 over v. Now, n over v. And we said that this should be equal to p over kt. So this tells me that PV is equal to nkt. Which is my ideal gas law. Basically, this tells me that the ideal gas law depends only on the assumption that the positions of my particles are independent of each other. I don't need to make any other assumption. Let's do another example. This is basically the most I can do without any further assumptions about the interaction, about the properties of my system. Let's look at another, a more particular system. Let's look at the quantum mechanical system of n particles confined in a cube of side length L. This is a cube. Believe it or not. Now, if you remember this, well, this is just nothing but a particle in a box problem. And if you remember the particle in a box problem, the solutions, the possible energies of a single particle, E1, were 1 over 2m h bar squared over h bar squared pi squared over L squared times nx squared plus ny squared plus nz squared. This is the energy of a single particle. So the microstates in this case, I can specify my microstates by specifying nx for the first particle, nx, ny, and z for my first particle, then nx, ny, and z for my second particle, nx, ny, and z for my nth particle. So this is my microstate. Now then the question is, how many of these microstates corresponds to a given energy? Now the total energy of my system is just sum over all the particles, 1 over 2m h bar squared pi squared over L squared, nxi squared plus nyi squared plus nzi squared. So the number of microstates is nothing but the number of terms in this expression. Sorry, this is a summation over I from 1 to n. So how many different integers, nx, ny, and z, for each one of the particles I can find that satisfy this relationship? That will tell me the number of microstates I have. But you see, let me just rewrite it a bit. This is E times v to the 2/3. Now this is L squared. So basically, how many integer sets nx, ny, and z for each one of the particles does exist that satisfy this relationship? You see, that number doesn't depend on E or V separately. That number depends on the product E times V to the 2/3. So omega, which is a function of n, E, and V, is actually a function of n, E times V to the 2/3. Now, this will give me some more relationships. Well, let me not call that omega, that number, that function some, let's say f. Derivative of the logarithm of omega, derivative of omega with respect to E is just derivative of, let me also divide by omega, this is 1 over f times the derivative of f with respect to its second argument times V to the 2/3. Derivative with respect to E at constant n and V. Derivative of omega with respect to n, this is 1 over f times the derivative of f with respect to the second term times, no, this is not n, sorry, that is V at constant n and E times derivative of E times V to the 2/3 divided by derivative with respect to V. This is 1 over f2 times E times V to the 2/3 times 2 over 3V. What was the derivative of, what was this derivative? This is t, 1 over kt. This is the derivative with respect to v was p over kt. So let's see, p over kt is just 2 over 3v times E times f2 v to the 2/3 divided by f. But this factor in parentheses is nothing but one over kt. Well, this tells me that, well, the kTs I can just cancel. E is 3 over 2 PV. And this was another relation that we had derived before. The energy of, well, it is for an ideal gas. Well, the relation that led to this conclusion was that we started from this expression for the energy. Again, this is just free particles moving in a volume V. So if you have free particles moving in a volume V, or in fact the only thing we actually use over here is that the energy of a single particle is proportional to 1 over V to the 2/3. As long as that relation is satisfied, you have this relation between energy, pressure, and volume of my system. I still don't know what the number of microstates is, but still just looking at some simple properties of that omega, we know that energy is related to pressure and volume through this relation. And for this particle, we also know that PV is NKT. So we know how the energy and temperature are related. Any questions? So let's just finish it over here. I mean, tomorrow we will go on and actually calculate this number of microstates corresponding to a given macrostate for this free particle, ideal gas, basically. So see you tomorrow.